Yeah, so welcome to the Tiny Tapeout 6 Bringup party. Woohoo!
Woohoo!
I want there to be like reactions like in Google Meet where if everyone clicks the party at the same time, it like rains parties.
I can rain PMODs.
So, Uri, do you want to show something to get the ball rolling? Woohoo!
Yeah, I can start. I have a few designs on Tiny Tapeout 6. I think we can start just with the obligatory Simon Says, because it's the quickest to get up and running.
Mm-hmm.
So, okay, can you see my screen with my cup of tea and my PMOD setup and everything?
Looks good to me.
Okay, so the first thing you do when you get a TT6 board, you are going to connect to it with the Commander app. And whoops, I actually have a surprise here. It's TT7. So I will plug the right board. That's the first thing you need to do. You need to
I made exactly the same mistake yesterday.
You did? So I'm not alone. So let's plug this TT6 to the right USB connector, to the correct one. And now let's try it again. So yeah, now it says TT6 and I can see the factory test running. You can see like the 7-segment counting up. And if you want it to be real fast, we can change the clock, let's say to 30, set, and now it should be doing faster. I don't know if it's probably the camera is too slow. Let's try it the other way around. Set it to 1 Hertz, and now it is slow as it should be. Okay, so for Simon, we need to plug the PMOD, which includes the game interface. So this one, and oh, it's difficult to plug this 3-port PMOD, but I managed to make it work. And now we can test the game and see how good I am at memory at 7 p.m. So select the project, set the clock, and you can immediately spot that there is something wrong here. Can you hear the bzzz? Because
yeah, it comes through nice and loud.
Reset it. Yes, I need to reset it. So that's the most common mistake for my own. I've been doing on my own project, just wondering why they don't work because I didn't reset them. But now after resetting it, it actually behaves and we can test it. So let's play a game. That was green. Green and blue. Green, blue, green. And obviously, we can make it more fun when we fail. Okay, so the game works, especially the amazing sound effects, but we can see that the score display is also working.
Cool, okay.
For TT9, I think I submitted an improved version where you could play the game like 100 moves or something like that. In the current version, you are limited to 32 moves, I think. So when we get to the TT9 live stream, I'm going to try to play and win like the high score of 100 score points. Let's see how many people will hang through. So should I do another one, or do you want to do something? And
yeah, do you want to do one more, and maybe we can ask for volunteers from the lovely audience who'd like to show something, so we can work out who's going to go next after you. You show your next one.
Okay, so let me just get my logic analyzer set up so I can show some one of the, in my opinion, more interesting analog. Okay,
well, tell you what, while you're getting that set up, I'll share something I've got ready here, and then we'll get Pat on. Pat's got something to share.
Perfect.
So I'll just remove you here. Okay, so I've got Tamas's Flash ADC. Also, just to show a cool thing that Uri's added recently is you can always access the 3D viewer now directly from the from your project's page inside the Tiny Tapeout website. So this is just going to show us on the output for all these. I think it's a 4-bit Flash ADC. So we're going to get some outputs on the output, binary bit 0123, depending on what's going on the input analog pin. And I have here maybe I can put that there so you can see it. You can see the segments flickering on and off. And if I just bring up the signal generator, you can see that that is generating the signal, and that's then affecting what we're seeing. So congratulations, Tamas. That's looking good. I'll submit report results. I know you've already tested it, but it's good to have more people. And then I will remove this and then add Uri back. Are you ready to show something, Uri, again?
Okay, yes, I think I'm almost ready. I will just have to remove the PMOD and connect my logic. Go quiet. So we will be testing oscillating bones, which I guess Matt will show you the layout of the design in a few minutes. So first of all, let's check out the pinout. It's very simple. We have 4 outputs, no inputs, and it's just a ring oscillator. And we are going to look at output number 3, UO out 3, which is the oscillator divided by 8. I think we are expecting a frequency of 20 megahertz-ish there. So let's just connect it to the ground and then to the other cable to pin number 343, starting from 0. Okay, and now I plugged it. Let's go to the logic analyzer. Oh, did I select the design? Yes, now I did. And now we can go to the logic analyzer and okay, start a recording. You can already see like there is some kind of faint output. I'm not sure if it's because of the oscillations, but we will see in a moment. So channel number 0, let's start recording. And yes, we can see there are oscillations, and if we zoom in, we can actually see the frequency, which is around, interesting, 10.8 megahertz. Oh, I think it's because I set the threshold voltage wrong. Let's try it again with 3.3 threshold voltage. And let's see. Yeah, still 10.87 megahertz. Oh, actually, that's fine because that's the frequency divided by 8, and I expected the original frequency to be 80 something. So this is as expected. We could measure just the pin next to it, which outputs the frequency divided by 4 and not by 8, and then we will see the 20-ish megahertz that I expected. Let's try that. Just record again. And yes, now it's 22.7. So I think from simulation, I had around 90 megahertz undivided. So it's pretty close to simulation. a little bit slower, but maybe if I raise the supply voltage a little bit, which I don't have the setup, but maybe Silvani or if someone else on the stream has the setup where they can change the supply voltage, we can actually see how the oscillation frequency changes when you change the supply voltage.
Or heat, maybe.
Or who?
Heat it up.
Heat. Okay, cool.
Yeah, so you were talking about your layout. So I actually went ahead and got something ready to share here. So if I share my screen again, this is what we got on the background. No, this is something. This is Tiny Tapeout 6. And I want to just put a shout out to Texplained for doing our decapping for us. Really nice quality here. You can see the Open Hardware logo and the Caravelle logo.
So that's the stuff that is added by eFabless. We don't
do
this.
Open frame, yeah. So the pad frame is what eFabless give us, and then the middle chunk is what we submit with all the designs. And then this is with I thought I had got a version without the... Okay, and then this is a zoom in on that design oscillating bones.
Yes, you can actually see the ring. So the skull in the middle is just a piece of art, but around it, it's hard to see in this level of zoom, but you have like a circle of transistors, of inverters. Each one is also shaped as a skull. And there are 21 of those, and they are connected in a ring, and that's what is creating the frequency that we observed in the logic analyzer.
Yep, and yeah, I don't know what happened there. I think I must have overwritten the JPEG that I was hoping to show, or I just put it on the background. Where is it? This one. That's the one I want. There we go.
Yes. So
this is with the metal 5 removed. And there's Uri's skull design there. Here's Pat's ADC.
Yeah, if you rotate it, you can see it spells ADC.
Yeah, ADC with a PSY for psychogenic. So, having said that, we've got Pat, I think, is ready to join the stream now. So I will add you in. Hi, Pat. How's it going?
Hey, Pat, good to see you.
Hey, it's the Bringup party. Yes. How's it going?
Yep. Let's put on the party hats.
In the background, that's where I got the Tiny Tapeout 6 decap. So, Pat, what have you got for us?
I have got actually another ADC. I finally got to play a little bit with that Wawa you were showing. And what I want to do actually is show that, but also show a little bit of my setup just for anyone else who wants to play with what I have. Can you solo me so I can show these images? Boop. Okay, so yeah, basically I have a TT06 board, except that it's connected with this front plate here, which gives us access. I only plugged in the B side, but anyways, I have all the Bs. And then in the front of that, because the RP2040 isn't the fastest thing in the world, I stuck an FPGA here that I can talk to and see things through the serial. So yeah, I guess we could try that. So this is the TT demo board. I've got that here, and I've got the FPGA here. So what I can do is, whoops, stuck in the FPGA. So load my project. Now because I'm piping through serial, I'm not going to go too slow, and it actually makes it a little more precise. So let's see, UART bridge. So now I'm just going to monitor with the FPGA what's coming out, and you can see on the scope here in the top right what's going on with the ADC. So I'm just going to go over there and actually play with the voltage a little bit. Yeah, it's just saying polling because it's getting zeros. So right now, let's give it some juice. I don't know what's happening, but we should be getting numbers.
Yeah, we see you.
All right, 0.7. So around 0.9, it's pretty precise. Let's go to 0.9. So that's that. It should be pretty close. It works okay, but yeah, when you get up high, it starts messing around. Now I'm at 1.7 and 1.6, and it usually doesn't react too well. But I can change this, and you can see something that's neat with the scope here is the purple trace is what's going on with the bits. It's a SAR ADC, right? So it's trying the first bit, and if it's not higher, it goes down one step, down one step, down one step. And if I increase the voltage, you can see it goes up, up, up instead. So you can see all those blobs. The blue is the comparator output, and it acts kind of funny towards the end of the sequence, but at the beginning it works really well. If I go up to, let's say, 0.9 here, or 1. So yeah, and then there's a transition. Oh, we're actually higher than half. So that's pretty cool. And that's it, really. Okay, let's break out of here. So I have my setup, and let's see, as I showed you, and we also have the cam there that we can look at a little closer if there's something to do with the scope. And that is my presentation.
Pat, can I ask you a favor to use your setup to test my charge pump?
Yeah. Are you on B? That would make it easy.
I will let you know in a second. So we have this pin out tab in Commander where you can see like your output, and I am on B2. Okay,
so tell me what I have to do.
So all you have to do is just select a charge pump. That's my project.
269.
And then you need, and then you need to maybe share a pet screen so people can see what he's doing.
Okay, and then we just look at what's happening to it, or we set the UI to something.
So after, Matt, can you share Pat's screen so people will see the results?
Pat's got like a OBS system set up.
So make him
yes. So
after,
shuttle.
So that's like the SDK way of interacting with designs. So after,
hold on a second, I'm going to turn off the power here because
we don't want to. So after enabling the design, I want you to ramp up the clock. So let's clock it at 500 kilohertz, then 1 megahertz, then 2 megahertz, and check the voltage at the output.
Check the voltage at the output.
Yes,
okay.
I think the output voltage we're seeing is the output of the pump divided by 6 or something like that. So we should see something like 1, maybe 0.8 volts or something like that, which means the pump is actually going like to 4 or 5 volts.
Which
B2,
B was it that I have to monitor?
B2.
B2.
And Pat, if you can wave your hands around in front of your scope camera, because Sylvan's saying he thinks your camera's feed is frozen.
Oh, it seems to be frozen.
Yeah.
Yeah. Okay, well, that's interesting.
Frozen.
That is odd. Because the image is jiggling. Hold on a second. Let me set up B2 first.
Oh, we saw your, it's going now. It's going now.
Okay, B2 is this guy. And I'll put this.
Yeah, nice setup you got there. I was planning to show it just by holding the jumper, the header pin on the like a UFL connector, but then I saw you got this cool setup, so I decided to take a ride.
So Vmax. There you go. Oh, yeah, that's probably too small for you. But anyways, Vmax is being measured, B2. And now all I have to do is clock it, right? And we see if this goes up.
Yeah, let's try to clock it like at 500 kilohertz, something like that. And then at 2 megahertz and see if there is a difference.
Clock project PWM. So 500K?
Yes, let's start with that. It should generate some voltage, but not like the highest. Do we see anything?
That is still like 40 millivolts. Am I really on B2? Let me double check that.
Double check it, please.
0, 1, 2.
I think your camera's frozen again as well.
Pat's camera?
Yeah. Okay, it's purple. And it's frozen again. Okay, let me see if I can just make this simpler.
Matt, maybe you can share my screen for a moment. In the meanwhile, say a word or two about the design, so we'll have some context. So this is what a design looks like, and it's basically a very simple charge pump. So what happens is we charge all of those 3 capacitors, and we use like those transistors to change the voltage at one side of the capacitor, and then we pump up the voltage as we go throughout the sequence of these 3 capacitors. And the thing is, we are running on 1.8 voltage from the supply voltage, and then we double it and we triple it, so we get around 5 volts because we lose some voltage because of the transistors here that functions as diodes. But anyway, we get around 5 volt here at the output, but the problem is that the analog pins can't really handle 5 volts. So what we are seeing here is actually a very big voltage divider made out of very long resistors in the, I think that's the polysilicon layer here, this pinkish thing. And then the output of that divider is going to the analog pin. So 1.8 at the input, then doubled, tripled, then divided, and then goes to the output, which Pat can hopefully show us now. Pat, are you ready?
I'm looking. I'm pumped it up to. Oh, I'm not on the right connector. Derp.
Okay, that explains a lot.
Yeah, I should have been more sensible when I was putting these. When I was hooking these up, because.
It looks like your camera's frozen again, because we can see from one view you bent over the workbench, but from the other view you're disappeared.
Well, my setup really sucks. I went to.
Let's put this to one side while we iron out the kinks, because Leo Moser is waiting to show a design. I want to bring him on the stage. So we'll come back to the charge pump.
We will.
Yeah.
Hi, Leo. How's it going?
Hi, everyone. It's going good. Yeah. How are you doing?
Good to see you.
Thanks. Yeah.
So you've got, what have you got to show us?
Yeah. So this is my setup here. Yeah, we have the demo board here. We have the TinyVJ PMOD. And we have my design. This is called Tiny Shader. And yeah, so the first thing, as you can see, it actually works. This is a relief, but this is not everything that it can do. So basically, this is just the default setting. But yeah, a few hardwired gates could produce the same thing. But the idea behind Tiny Shader is it basically replicates how modern GPUs are working. There you have a so-called fragment shader, which is a program which you write, and this will be executed for each pixel of a primitive, like a triangle. And this program will then determine what color this pixel will actually get. So you could look up a texture, or you could calculate the angle from the normal vector to the light vector and do some shading with that. That's how it works in modern GPUs. And basically, I wanted to replicate something simple here. And the animation that you can see here is generated on the fly. So for each pixel, my shader execution unit, that's how I called it, executes 10 instructions and then just draws the final color value for the pixel. So yeah, that's what we can see here. But the cool thing is that we can actually upload a different shader. So let me just try to do this here. Okay, so this is now a different one. We have some moving sprites, as you can see. And while the screen is black, yeah, a new shader is uploaded. We have a crosshair moving. See another one. And yeah, you can really see what kind of complexity you can do with 10 instructions and how the shaders can look like. So just created a handful of shaders just to show this off here. And yeah, this one is a bit more complex. I also have one instruction with a sign lookup table. So this one is nice.
Can we see like the programs that are running on the like this circles one? I really like it.
Yeah. So everything is in the repository. That's the final one. I call it Hypnotoad. So inside the repository, so you just go to TinyTapeout 6. Maybe, I don't know, should I share or can anyone take a look at this?
If you can, yes, please.
Yeah, you want to? I mean, I was having a look at the repo earlier, and the design, it looks great. But I wanted to know if I could write my own shader.
Yeah,
just use
that's for sure.
ChatGPT. It will write it for you.
Probably hasn't yet crawled the data. So can I? Yeah, I can try to share.
Yeah, I'm looking at it right now. If you want to share my screen, I got it open, Matt. So they seem pretty simple.
I think I'm sharing now. Can you swap, Matt?
We got you.
Yeah, we see.
Yeah, all right. Yeah, so this is the repository, and here I have some examples. So these are some instructions. So we have 1, 2, 3, 4, 5, 6 instructions for this simple shader here, up to 10, of course. And you have 4 registers that you can use, R0 to R3, where R0 is a bit special. And yeah, that's it. So here you get the current X coordinate of the pixel. You put it through the sign lookup table, write it into R1, and you set the R value for this pixel to whatever comes out of here. And yeah, you do the same for Y and set it to the green value. And this produces this pattern here. And there are also some other input registers. There's a time register. I think I mentioned it somewhere at the bottom, which increments at 7.5 hertz. So that's how you can do these moving animations and that stuff. And yeah, and also those other with the circles, these shaders are also all in the software directory here. I wrote a simple assembler which just generates the binaries. So we have the shader files all in here. We just run this makefile. And also it produces some images. So it actually emulates the shader and gives you an image, so you can see if it will work or not, and then you can finally upload it to the real thing. So
Very
yeah,
cool.
I think there is also a GIF animation render, which is cool.
Yeah, that's just a whole range of images then put together.
And all of this fits in just one tile.
Yeah, exactly. So that was my challenge. And the cool thing is, I think, yeah, the first step when you're doing a tiny tapeout, you try to just get your design working. But now I'm trying to resubmit this design to TinyTapeout 10, and actually with clock gating, for example, I can increase the number of instructions to maybe 16, and then I can try to run the shader execution unit at maybe double the rate of the VGA frequency. So I should be able to both increase the resolution but also the number of instructions, and that will be really a lot of fun. But it actually shows how the more your skill increases, the more actually is this one tile worth to you, and this is quite interesting, I think.
Yeah, it was great seeing that happen with the demo scene competition. How much stuff people can fit into just one tile. This is a really nice demo. I'm definitely going to write my own shader.
Yeah, I'm looking forward to this. Yeah.
Yeah. Great. Okay. Thanks very much, Leo, for sharing your design. And we've got Jonathan Hager, who's coming on next. So thanks again for sharing.
Thanks. Bye.
Hi, Jonathan.
Yeah. Hi, I hope you can hear me.
Yep.
Yes.
Okay, so first of all, Leo, very cool design. Some friends of mine are currently doing their own graphics card. It's very interesting to see that happening on a tiny tapeout. So I'm from the University of Würzburg, and we are mainly doing the tiny tapeout to have something to show students in the lecture and to show how chip design works. And we are currently looking into bringing students to the point where they can do their own tiny tapeout. So on this chip, we did a small CPU, which we are doing in the or which we are using for teaching in the lecture. And I can show my screen, hopefully.
It's the little icon at the bottom that looks like a first aid package.
I'm just looking for the right one.
There we go.
Yeah, perfect. Okay, so Christopher Batten developed this tiny RISC-V1 subset, which is very small, only has like a few instructions, but it's very comfortable to use in the lecture. And we did a RISC-V CPU on this tiny tapeout for this one. And I prepared a little demo to show here. So it's just a simple program which calculates the Fibonacci sequence. So we have a base address in the memory where we want to store the numbers, and we have like a few counters and registers which are used for computing them. And I had some problems getting the communication going. So we have a SPI interface which acts like the memory for the CPU, but I prepared a little demo here which I can show. So I've got everything hooked up here. I've got a logic analyzer here which we can see, which we can use to monitor the SPI communication. And I prepared a little MicroPython test bench which will just run this assembly program here.
Assembly program.
Yeah. So let me just start it. It's quite slow on purpose, so you can see what's happening. So here we can see that the CPU is fetching all the instructions, and it's reading and incrementing its addresses. And now we've achieved the first Fibonacci number. And it's looping around, so we jump from address 12 to 6, and then we got the next one. And
so the RP2040 is actually emulating the RAM for the CPU, the RISC-V core that is running on the Tiny Tapeout 6, right?
Yeah, exactly. So
cool.
This is designed to be used at 12 megahertz because we have some FPGAs here which the students use. But for this demo, I just wrote everything in Python, so you can have like a bit more output and see what's happening actually. And I think we are finished here. So this is just the endless loop at the end, and then it will dump the contents. And we can see that the memory at the beginning just contains the program, and here the Tiny Tapeout CPU calculated the first few Fibonacci numbers. And with the logic analyzer, we can show, which is basically the goal for the lecture, we can show how the communication works. So we can see all of these SPI transactions with the chip select going to low, and then the CPU requesting some address, and the firmware responding with the corresponding data. And yeah, the goal for the next Tiny Tapeouts is that students can submit their own design. So that's very cool that this is possible. And the design here is quite large, but I think we can fix this in the next few shuttles.
How large is it?
It's 3x2 tiles, so 6 tiles.
Yeah, now we have like 5x4, so you still have plenty of space if you want to make it larger.
Yeah, I think it mainly depends on the students' project. So this was just our implementation, which we tried to get running to see if it is actually doable. But it works, and we can show it in the lecture. That's pretty cool. And I really hope that some students are interested enough to learn the entire Tiny Tapeout process so that they can get their own chips running.
Awesome. I see that the design is not listed as being tested yet. Are you planning to submit a test result?
Oh yeah. I will just do that. I will also upload my test bench here.
So that we can replicate it. Yeah.
Yeah. So I only got to test it in the last few days, and I didn't report that yet. But yeah, I will do that, and I will upload all of this.
Just to show people, we've got this silicon proven projects here now that you can filter by shuttle, which is pretty real time. So I think I just tested the Flash ADC, so my test result has just come in here. So if you add your designs as you test them, they'll show up on the silicon proven projects page.
And other people can also test your design, and then it goes to the top if many people test it.
Awesome. Okay, thanks very much, Jonathan, and best of luck with getting the students interested. Let us know if we can support you in some way doing that.
Yeah, thank you very much. Thank you for doing the Tiny Tapeout. Very cool initiative.
Thank you.
Thank you.
Okay, Pat is back. We've got Mike Bell is ready to show MicroPython. I've invited him to the studio. So Mike, if you're listening, you need to accept the invitation so that we can bring you on. But while we're waiting, Pat, did you want to show us what you've got with the charge pump?
Yes. Check this out. Okay. So there is...
two.
Okay, and what I'm going to do is this, actually. So all I'm going to do is loop around. The project is loaded, and I'm going to clock it and wait a little bit between each one. So let me bring back the VLC so we can see that. Okay, now it's ramping up.
Yeah, we can see the voltage rising.
Yeah, so you can see little interruptions apparently when I change the clock rate. It seems to stop for a little bit, and then it just drops, boom. But it goes up and up and up. It seems to top out around, I don't know, let's say right now it's 100, what is it? It's 1 megahertz. And it's just not going. If I clock the project at, 3 megahertz, there's not really... there's a little impact, but it's diminishing returns from there on, from about 1 megahertz.
If you go up to 20, it will probably start going down at some point.
Let's see. Not bad.
Yeah, it's not going down.
You're saying it would filter? Yeah, it's up at 30.
I'm impressed with my own project. I think it's 40. It's like starting to hit the limits of the... No, I can actually go up to 60. That's like the limit of the
let's do it. 62, I think. And it didn't crash.
A little, right?
Maybe, yeah. Hold on.
Drop, but it's like I think around 2 megahertz. Let's try
30.
2 or 3.
There's 30. So
yeah, I
hardly
see a
anything.
small. Yep. So it ramps up nicely until around 1 megahertz, and then going.
Let's see.
It's pretty flat.
30, 60.
Okay,
Anyways.
so
Very cool.
we got Mike ready now. So I'll add Mike. How's it going, Mike?
Hey, man.
Yes, okay. I
Hello.
think, is that
We can hear you.
working? Hello, hello.
Yeah. Hello.
Excellent.
Welcome to this stream. And just before we get started, if anyone is watching and wants to show their design running or want us to test it on the stream, just let us know in the comments so we can queue you up. And the coolest thing about these streams is that we show your designs working, not our designs. So if you've got stuff you want to show off there, just please let us know in the comments. We'll invite you on. So having said that, I'll maximize you, Mike.
Am I backwards to everybody? Or is that...
You look good to
The
me.
screen is fine.
Okay, cool.
And you're
if I look
fine.
at it here, it looks mirrored, but that's all cool. Yeah, so I want to show off TinyQV, which is my second RISC-V processor I put on Tiny Tapeout. So I tried to learn quite a few lessons from the one that was on Tiny Tapeout 4 and put together something a bit more kind of extensible. And I'm continuing to work on the design up to Tiny Tapeout 10. I've got a new revision coming up, but so let's have a look at it. So I've tried to put together some...
I see you are also using the PMOD, the bonus PMOD from Tiny Tapeout 5, right? The LED matrix display.
Yeah. So we wanted
Very
to...
cool.
Yes, so we'll demo that in a bit. Yeah, so I've put together some kind of instructions here on how to get your own programs running on TinyQV. And over the weekend, I was working on this programmer here. Oh, I've got the board plugged in. That'll help.
So this is actually, you took our Flasher application and you just forked it and created your own version that is suited for the TinyQV, right?
Yeah, that's right. So TinyQV, I was trying to minimize the size of it. It manages to fit in 2x2 tiles. So one of the things is it doesn't contain the commands to actually set the flash up and the PS RAMs up. So that's done by the RP2040 before it starts. So it needs a slightly custom setup on that. So yeah, I made this. Let's see whether we can get that to work. Let's try again. So yeah, I changed the flasher a bit.
That's cool. When I made the Flasher, I really hope that people will just fork it and create their own version. So you are the first person to do this. Thank you.
It worked perfectly the other day when I used it, apart from me plugging the wrong board in.
I think the LED matrix, it goes full brightness and then it may drop the voltage and cause some issues. So maybe you want to disconnect
Yeah, maybe
the power.
I'll disconnect that and see
for
whether
it.
that helps.
Now it looks better.
Ah, that's better.
Huzzah.
Right, we're in. So yeah, if you go to this TinyQV programmer, the links in the repo, then I've got some kind of example firmwares that you can just flash and run. So we've got Hello World. So when you say
Write
flash
them
and
all.
run, yeah, that just writes it to the QSPI flash on that PMOD there, and that runs it. So you can see that output coming from TinyQV. So that's writing out over UART, and the RP2040 on the demo board is reading that. So we could do digits of pi. So this is one of Bruno Levy's programs. He's got a collection of small programs that are kind of designed for playing around with RISC-V designs.
Users can find the source code in the TinyQV repo, right? Of all those like
Yeah, so
Lord
there's kind of a collection of repos. So I've got the custom RISC-V toolchain that you need for building it. The TinyQV SDK, which contains the files you need to boot the board and interact with the UARTs and the SPI peripherals, and the GPIO. And then TinyQV projects has got a few binaries in there. And then I've also got MicroPython up and running, so there's a link to the version of MicroPython there. So I've also got MicroPython. You can just load it through here. So let's do that. This will take a little while to flash. It's what?
How are you doing that? Are you dumping a driver through the REPL and then just running it with the data?
Yes, that's right. So it's just a script. It's Yuri's script that
Heavily modified.
Well, so I did some changes to. I used DMA to write to the Flash, so it's a bit faster than it was. Yeah, it's basically the script that Yuri put together for piping the binary file out from the web app to. So
let me just get it right. We are using MicroPython on the RP2040 to write MicroPython to the Flash in the PMOD, so we can run MicroPython on TinyQV in Tapeout 6.
Yep, it's MicroPythons all the way down.
MicroPython inception.
So yes, this is now MicroPython, my customized version of MicroPython running on TinyQV, running on the ASIC. We can do stuff like do some maths, and that works. But more interestingly than that, maybe you might notice I've got this SD card PMOD plugged in. So I think I might be the first person to use one of these headers on the side of the Tiny Tapeout board that Pat put in. And that's really handy because it prevents a whole bunch of wiring to the SD card, which makes things a bit more reliable and neater. So the
probably
SPI,
also the first person to use an SD card with Tiny Tapeout.
Yeah, maybe, yeah. So with a bit of luck, we can get to the SD card running in MicroPython. So
do you have like a file system there or something?
Yeah, so MicroPython has integrated drivers for reading fat file systems. So the great thing about getting MicroPython running is that suddenly you can access all of that stuff. So because I can just compile C programs for the RISC-V chip, you get all those abilities from MicroPython. It's taken a little bit of kind of finagling to actually get things running.
The hardware abstraction layer. Did you expose the I/O?
You just need a SPI interface to interact with SD cards. So I've got a hardware abstraction layer that I've written for MicroPython, which exposes an SPI peripheral. It's got slightly different arguments to the one on the RP2040, but once you've created it, it's just works like the SPI peripheral on any MicroPython device. So therefore, this SD card driver that I've just loaded is a Python script that's frozen into the MicroPython firmware for TinyQV, and that's just from the MicroPython lib. So in theory, kind of any MicroPython device driver and that kind of thing, providing it just uses kind of basic SPI stuff, should be able to work with TinyQV like this.
So like an LCD display, for instance, or this LED matrix.
Yeah, absolutely. So we'll show the LED matrix in a minute.
Oh, nice. So you got the programs inside the SD card, and now we are going to run.
Yeah, exactly. We can see the file system on the SD card. We can read a text file from the SD card.
Party!
How fast are you clocking this?
So TinyQV is clocked at 64 megahertz. The SPI or the QSPI interface to the PMOD's 32 megahertz, because that's basically the limit of the outputs on Tiny Tapeout. And actually, I looked at the clock, and at 32 megahertz, it looks really quite dodgy. Some of the clocks only getting a little over 2 volts, and that seems to be working. But if I go even up to 70 megahertz, so 35 megahertz clock coming out on the output, it stops working. So I don't know if that's just my hardware. It might be interesting to compare different people's chips there. But yeah, it seems quite close to the limit, just on that 33 megahertz limit there. I don't know whether maybe there's something inside my design which is influencing that.
Did you submit a design to one of the IHP shuttles as well?
Yeah, so this is basically this version of TinyQV. I think I added a PWM peripheral, which I wanted so we can try and play some music through it maybe on the IHP one, and that will be on Tiny Tapeout 10 as well.
Yeah, it will be interesting to compare like the speed of the IOs there with the Sky 130.
Yeah, Sylvan, I posted, it was a little while ago, I was posting about those that clock output at 32 megahertz, and it's kind of barely making it over 2 volts. So yeah, we can dig into that again. And I was going to get it set up so I could see how much current is being drawn, but I haven't got around to doing that yet. So yeah, more investigation there. But for now,
let me know if you want me to run
working.
any tests, like to compare chips.
Yeah, that would be cool, just to get an oscilloscope hooked up and see what the SPI is doing. No,
Matt, can you zoom in on Mike's screen so we can see what he's doing there?
So this is just basically proving I can write a file, and then we can read that file back again.
Call it betapple.txt.
So yeah, this is just writing some numbers. We can read those back. So yeah, we've got IO, and I've checked, renaming files, deleting files. That all works as you would expect in MicroPython. So yeah, the file system's really working.
You just got me thinking. So if you got a functional SPI interface, then you could probably interface the same chip that they use on the RP2040W, the CIW43 for the Wi-Fi and Bluetooth, and then if there is a driver for MicroPython, it will be the first Tiny Tapeout IoT project ever.
Yeah, I was actually wondering, even with NanoV, I never got around to it, but I was wondering whether you could interface one of the ESP chips just using the standard UART interface. That should definitely be possible. But yeah, the RM2 modules for the PicoW use a slightly weird interface, but I don't know if the breakout exposes. They use a slightly weird interface where the same pin is used for data in and data out, so you need a bidirectional pin.
Like with a resistor that makes the
maybe you'll be able to make it work. Yeah, that might be worth that. That would be interesting, definitely. So yeah, I was just gonna I've got some Python files in here. So this is a super simple one. We're just going to flash an LED on and off. So if I just execute that, hopefully you can see that flashing.
Yep.
I put a bigger LED on, so hopefully it's a bit more visible.
We can also see like the dot in the 7 segment flashing.
Yeah. So I've got most of the I/O busy here. So or the output PMOD in particular. So
which
SD
IOs
card
are available for the user?
So yeah, the UART is using outputs 0 and 1. So 0 for the transmit and 1 for the flow control, because there's only a very small buffer, like 1 byte, on the TinyQV UART. So it needs to have good hardware flow control, and we had that bug where pasting things in didn't work because I mucked up the flow control from the RP2040. So yeah, 2 pins for the UART on the output, and then 3 pins for the SPI for data, clock, and select. And then I've got the that LED matrix we're going to show in a minute on another select on the SPI. So that only leaves this the one final pin out 7 for the LED there.
It's enough for a Blinky. That's all you need.
So yeah, let's try plugging this LED display back in. Hopefully it won't crash the board. See if it's working.
It's now playing nicely.
There we go.
TD6.
Nice.
Amazing. Let me clap.
Yeah, so what else did I have on here? I think we got a final message for you guys. yeah, this Max 7219 driver is just, again, a standard bit of MicroPython library code. Matty
You didn't have to write it.
Yeah, exactly. So that's the great, as I was saying, that's the great thing. I didn't have to write the driver for this display. It's just a standard driver. I've got some error to do with garbage collection here, but it's still running, so that's good.
So nice. And how much?
Really cool.
You got 16 megabytes of RAM as well on this MicroPython?
Yeah, that's right. So I've limited the garbage collection heap to 1 megabyte because when it's using 16 megabytes, when it decides to do a garbage collection, that's really slow, and you don't need that much memory. It's a very slow chip compared to like the RP2040 even. So yeah, you just I decided to limit it to 1 megabyte because that's more than what you need, really. Yeah,
I'm impressed.
Thank you.
Very impressed.
So yeah, hopefully
Excellent.
people can play around with that. It'd be cool to see other people using it. But yeah, it's been really fun to put together, and yeah, as I said, more experiments to do on it as well.
Fantastic. Thanks so much, Mike. Really great project. And yeah, I was also testing the C SDK out on the stream yesterday. So
Cool,
that
yeah.
worked very nicely as well. So thanks for putting together the great instructions. Okay, so I've also remembered that I've got a remote entry to the stream. Anton wanted to show his analog VGA design, but he wasn't able to attend in person. So he recorded like a 2.5 minute video. So I'm going to play that now.
Hi everyone, Anton Morovic here, or AlgoFugle. My submission to Tiny Tapeout 6 was TT06 Grab Bag, and it's my first mixed signal, and in fact my first analog VLSI design. At its heart, it implements a true color 24-bit VGA driver, so that means 8 bits per each of the red, green and blue color channels, more or less. It looks much better than I expected, thanks in no small part to a lot of assistance from Sylvain. I learned the essentials of doing both the design and the layout from the 0 to ASIC analog course. I took a fairly primitive approach by implementing 3 R2R DACs, which were inspired by the example that Matt includes in the course, and I just sized them for higher currents and a 10 kilo ohm output impedance. The DAC's input comes from a digital control block hardened with OpenLane, and it implements some basic modes including a pass-through mode, ramp generator, and some pretty XOR patterns. The output is weak though, due mostly to the basic R2R DACs. I cobbled together a VGA triple op-amp board, later doing that as a better prototyping PCB. I hooked it up, but I was getting poor performance. While I'd simulated the design for a slew rate of about 240 nanoseconds, going from full brightness to black, it was actually at least 4 times worse than this, leading to some bad smearing horizontally on the screen. That's where Sylvain stepped in and gave me some expert tips. First was to get rid of the coaxial leads that are plugged into the UFL connectors and instead just use hookup wire directly. More significantly, using 2.2K pull-down resistors to ground from each of the color channels reduces the effective impedance to about 1.8 kiloohms instead of 10 kiloohms, which got me a much faster slew rate on the input side of the op-amps of about 80 to 100 nanoseconds. There is one clear mistake. OpenLane sizes the digital output buffer standard cells differently, meaning that they're not matched, which it maybe does for digital timing reasons. This is probably the main reason I have a discontinuity which becomes obvious in the ramp modes. But stay tuned for the Tiny Tapeout 8 version, which takes a completely different design approach. In early February 2025, I'll put up schematics and detailed testing results. I'm working also on a new neat interposer board that you could fab for yourself if you really wanted to try this design out without making a mess of your TT06 kit. Hit me up when you'd like to see all of that, or if I otherwise seem to have forgotten. Thanks to Matt, Uri, Pat, Sylvain, Stuart, and anyone involved in Tiny Tapeout, including the community, and thanks also to eFabless for their part in sponsoring Tiny Tapeout and doing the chip fabrication. Great work everyone, and I look forward to many more Tiny Tapeout chips in future. See ya!
Hi, Tom. No audio. We can, while we try, do you want to, I don't know, see if you can, no, I can't hear you.
No sound.
No sound.
At least we got a teaser for Anton's video. He will probably upload it to his YouTube channel, right?
Yes. Yeah. Apologies. I don't know what's going on. I'm running on all the latest stuff that is meant to be good for StreamYard. So it just crashes the browser tab. So apologies. I can't play the whole thing there. And Tommy, I can, even if we can't hear you, do you know like sign language?
You can mime it.
Well, let's finish off. Thanks for trying anyway. I'll share my extra camera here, and hopefully this won't break. Solo the layout. And I try to get Tom's design working. Let's see.
That's a nice tiny VGA screen that you got there.
Yeah.
Tom says you need i7 on, input 7 on.
Okay. And it's called...
Connect to the correct one. That's what happens when you have too many tiny tape outs on your desk.
So this is tennis.
Yep, VGA experiments with tennis.
Why is it searching for just N?
It's a clever AI, that's why.
Okay,
And
I got something on the screen
7.
here.
Yeah, now we'll toggle input 7.
Input 7. All right.
All right. Too bad you don't have the controller PMOD yet.
Yet.
Can I can drive myself up and down though?
I
mean, you are winning, that's fine, right? Maybe
that's the point, isn't
it? Yeah, it's the winning mode.
Where's the other side there? I don't see the other.
Where's the other panel? I thought the one was the other paddle, and I was like, oh.
Yeah.
Yeah. Maybe
Where's the
try
other
toggling
panel,
off
Tom?
pin 7 and see what happens.
Yeah,
Tell
I
us
think,
in the,
your screen is cropping it.
Yeah, it's a tiny VGA.
Yeah. Tom, in the chat, tell us how we control the other paddle.
Yeah, he says it's
see it
missing.
anyways.
He says what? Sorry.
The paddle is missing, like the right side of the screen is cropped.
Oh,
But
you
he
just
says
probably
that,
can't
like,
see it because
read the instructions. That's what he says.
Okay.
Read the
Oh,
manual.
he's coming in.
RTFM.
All right. He's coming on the private chat. Okay. And we just got another person, Deanna, who wants to show her design, but not very fluent. So, but yeah, we'd love to have you on. So I'll send you the invite, and we'll see if we can get that working. Chrome seems to work best unless you're me, in which case it crashes your video when you try to upload it. So good job, Tom.
Yeah.
Can I unsolo myself? Exit solo layout. There we go.
Maybe while we are waiting for Diana, Pat, you mentioned the game PMOD. Maybe a word about that?
Oh, hold on. Here we
Yes.
go. Tom's sharing his screen now.
Ooh.
Now we can see 2 paddles.
Yes. Thanks, Tom. Good stuff. And yeah, just before we get onto the PMOD game, I see that Deanna's here as well. Hi, Deanna.
Hi everyone, can you hear me?
Yeah,
Yes,
loud and
welcome
clear.
to the
Yes.
party.
Hey.
Hi, I am from Colombia.
Bienvenida.
¿Qué tal?
Gracias. Okay, I'm going to share.
Deanna, your mic is quite loud. I don't know if you can turn the volume down a little bit.
Okay. Can you hear me? Okay.
Yeah, that's good.
So
yeah.
much better now. Thank you.
Okay, so I have here like a low effort diagram of what my design has. What I wanted was a design to process image. So my design has a grayscale algorithm and a Sobel edge detection algorithm. And I have an SPI interface to give as an input the pixels. And I have some multiplexers because I wanted to select different types of processing. So I wanted to see what I call bypass. That is what I give as an input. I wanted to see it as an output. And if I wanted to see only the grayscale process, that's what multiplexers are for. Or if I want to see only Sobel edge detection, or if I want to see everything like grayscale and Sobel edge detection. So right here I have like this is like my testing image, and this is like the Sobel edge working. It takes a while because the image is a little big, but the grayscale is only the grayscale process is a little fast than the Sobel. So it takes a while to see the result, but now we can see like the image in grayscale.
Very nice. So is it running on the Raspberry Pi that is like feeding the Tiny Tapeout 6 through SPI, or how does that work?
No. I didn't have the time to test that Raspberry Pi, so I use an external Raspberry to do all the like the arrange all the pixels that like my design has to how my design has to receive them, and I wanted to make work the Raspberry does in the test board, but now it's an external Raspberry Pi.
Which is also good. Like I think this is how Pat is working with an external Raspberry Pi, right?
Sometimes
and what's the
it depends
pixel
what I'm
format,
doing, but
like
yeah.
8-bit per pixel?
24 per pixel.
24
RGB.
bit, oh, RGB, yeah. RGB per channel per pixel.
RGB, yeah. But if you choose only Sobel process, you have to give the pixels in grayscale because Sobel works with the intensity of pixels. So if you choose only Sobel and you give RGB pixels, that will be a mistake. So that's why I incorporate a grayscale algorithm. But you can try of the different types of process that I design.
So this works streaming it one pixel at a time. It manages to detect I mean, are you in there building like a little kernel, a little matrix, or you're doing a stream?
Yes. For grayscale, it works like you give the pixel and it converts that pixel into intensity. But for Sobel, first he has to like store 9 pixels that are the neighbor pixels, but just for the first time. But then you only need to give 3 pixels because the other 6 are stored in the previous process. So I have to make like a state machine that controls that how store these pixels in the design, but you only have to store nine pixels that are the neighbors of the
Right.
like
So, but that
the
means
interested pixel.
you're not passing them in order like this as rows. You're passing little squares. You're
Yes,
kind of going like this.
Yeah, like matrix. I have to store as the matrix of the neighbors of the pixel that it has to
Well,
process.
it works really well. Good job.
Are you going to try it, Pat?
Yeah, well, okay. So your code there is running on the Raspberry Pi. Is it a 5 or a 4? Because I got this, and maybe that would have been helpful. But basically, a Raspberry Pi and a little connector that goes.
I don't have another camera to show my setup. I don't know how to show my setup.
Maybe you can take a photo with the phone and then show us the phone screen or something.
Okay.
That's pretty good.
Yes.
Yeah, I ended up doing this because it was such a giant pain in the butt to do. So I've got a Pi and then this, and then connected to the boards with that. So I'm wondering what kind of solution you used.
Give me a minute.
Sure.
I can show my
I just
setup.
use the poor man's solution always. No fancy PCBs in my case.
I ended up like that, and it was such a mess that it worked, but don't try to debug it. I actually had one wire crossed, and took me a half hour to figure it out.
And did you put like this script that you wrote anywhere on GitHub so we can try it too?
I don't know, but in the Discord, I can tell you or update my GitHub.
Yes, please do, so other people can also try it. And there is like the report button where you can put a link to write
I'd like to try it.
and put a link to the script so other people can also try it. I want to try it. And Mike Bell is asking if you are using the SPI directly from the external Raspberry Pi to talk to the design on the Tiny Tapeout chip.
Mind is occupied.
It happens.
Happens to me a lot.
Yes. Okay. So this is.
Nice.
Oh, you went
Sorry
the wire
for the
way.
mess. Yes.
No, but
Sorry for the mess, but and I forget to show the Raspberry Pi. But this extensor was really helpful for me. So this is how I
that
wire.
little T-bar with the
Yes.
ribbon cable. It's what I used for the first version before I had my little adapter, and it's a lot of
Okay.
wires.
You see, I don't even have that. You're spoiled.
We're old school.
So that's
Matt, we
it.
can't hear you.
Yeah, you're muted.
You
Matt.
are muted.
Yeah.
Okay.
Thanks so much, Diana. Really good to see that. Thanks for coming on the stream and being brave with your English. It's definitely good to have more people coming from other countries, and
Thank you.
appreciate it.
Buen
Thank you for
trabajo.
the opportunity.
Gracias para compartir. Okay, so let's call us a day then. Thanks very much, everybody, for joining.
Oh, I want to talk about the PMODs just 2 seconds.
Yeah, quick thing from Pat then.
We're doing the demo scene stuff and the games and blah, blah, blah. And we've decided to make it possible to use Nintendo-type controllers, SNES controllers. So there's these little PMODs, and they're going to support 2 controllers. They basically let you deal with them. It's not a complicated protocol. It's just that it's bidirectional. The SNES console goes, hey, give me the data, and then clocks it out. And that means that we'd have to use a bunch of BIDIRs or something like that. This instead has a CH32V003 on it, and so it just does the polling by itself, and it'll report all on the input side. So you can connect this into the input PMOD, 2 controllers, and then it'll just send you data whenever anything changes. And there's a little header on top that if you didn't want, it's only using 3 pins. So if you did want to use something else, you could stick it in there. So that's pretty much it with the stuff. I'm actually putting a page up, but I have already got some details on GitHub, and I'll post a link in the Discord for anyone who's curious.
Awesome. Okay. Well, thanks again, everyone, for joining. And I'll be doing like a little edit. Huh?
And eFabless for sponsoring this.
Yes, thanks, eFabless. That was Anton included that in his video, but then we never got to the end of his video. So what I'll do with the edited version of this is like cut out all that nonsense and put the whole video in from Anton. And yet, like Uri was saying, he'll probably share it on the Discord. But yeah, thanks again, everybody, for joining. Really super, super cool to see you all here at the end of the journey and testing your designs and showing them on the streams. Excellent. Really gratifying to see. Hopefully see you on Tiny Tapeout 10. And thanks for watching. Bye-bye.
Thanks. Cheers.